Ever wonder how pilots steer massive aircraft on the ground? It's all thanks to the nose wheel steering system, a critical part of ground control that ranges from simple to incredibly complex. Today, we're taking a deep dive into how nose wheel steering works, from light trainers to heavy jets. Let's roll. Most aircraft have a steerable nose wheel controlled from the cockpit. This system allows the aircraft to be maneuvered safely and precisely while taxiing, during takeoff runs, and immediately after landing. But not all aircraft use the same system. Some simpler planes rely on castering wheels and differential braking. In small aircraft, nose wheel steering is often achieved using a mechanical linkage connected to the rudder pedals. When the pilot presses the pedals, push-pull tubes transmit that motion to the nose wheel strut, causing it to rotate left or right. It's simple, lightweight, and highly effective for lighter aircraft. When it comes to steering massive aircraft on the ground, sheer muscle isn't enough. These giants need precision and power, and that's where hydraulic nose wheel steering systems come into play. Most large aircraft are equipped with powered nose wheel steering because manual control just won't cut it. And in almost every case, the system relies on hydraulic power to get the job done. While the designs might vary between aircraft, they all share core components and principles. The pilot controls steering from the flight deck, typically using a tiller, small wheel, or even a joystick mounted on the side console or side wall of the cockpit. Some aircraft even allow the system to be switched on or off, depending on the phase of flight or maintenance needs. That control input, whether mechanical, electrical, or hydraulic, is transmitted to a steering control unit, which works like a metering valve. This component routes pressurized hydraulic fluid to actuators that turn the nose wheel. The actuators use a system of linkages to rotate the lower strut, giving the aircraft precise directional control on the ground. Many aircraft also connect the rudder pedals to the nose wheel for small steering adjustments, especially useful during takeoff and landing when the aircraft is moving fast. The nose wheel steering tiller connects to a steering drum inside the flight deck pedestal. As the tiller turns, cables and pulleys send the motion to a control drum in the differential unit. This moves a link to the metering valve, shifting the selector valve and directing hydraulic power to turn the nose gear. Pressure from the aircraft hydraulic system is directed through the open safety shutoff valve into a line leading to the metering valve. The metering valve then routes the pressurized fluid out of port A, through the right turn alternating line, and into steering cylinder A. This is a one-port cylinder, and pressure forces the piston to begin extension. Since the rod of this piston connects to the nose steering spindle on the nose gear shock strut, which pivots at point X, the extension of the piston turns the steering spindle gradually toward the right. As the nose wheel turns, fluid is forced out of steering cylinder B through the left turn alternating line and into port B of the metering valve. The metering valve directs this return fluid into a compensator that routes the fluid into the aircraft hydraulic system return manifold. When hydraulic pressure is applied, the nose gear starts to turn. But to avoid turning too far, the system uses a follow-up linkage to control and stop the gear at the correct angle. As the steering piston extends, it turns the steering spindle. On the back of the spindle are gear teeth that drive a gear on the orifice rod, which rotates in the opposite direction. This motion moves follow-up links on the nose strut, turning a follow-up drum. That drum sends movement through cables to a differential assembly, which shifts the metering valve back to neutral, stopping the gear at the right angle. The compensator unit keeps pressure in the nose wheel steering cylinders at all times, so they're always ready, and act like shimmy dampers too. Inside the compensator is a spring-loaded piston and poppet valve. One port vents air, another connects to the metering valve return line, and a third leads to the hydraulic return manifold. When pressure hits 100 psi, the piston compresses the spring, opening the poppet and allowing fluid to return. This maintains a steady 100 psi throughout the system, keeping the steering cylinders pressurized and stable. Torque links on the nose gear help, but they aren't enough to stop shimmy, those fast, unwanted vibrations during taxi or landing. That's where the shimmy damper comes in. It uses hydraulic damping to keep the nose wheel stable. While some are built into the gear, most are external units mounted between the upper and lower struts. They work throughout all ground operations, without interfering with steering. Thanks for watching.